It is tempting to look back at the Second World War and search for the single, ultimate fighter or the perfect bomber, the one machine that outperformed everything else in the sky. American industry reached air superiority through a massive, overlapping portfolio of specialized airframes produced simultaneously. Maintaining dozens of separate production lines for different designs seems counterintuitive. If you have the industrial capacity to build anything, why not standardize the single best machine? Aviation design is a zero-sum game. You cannot maximize every trait. Adding heavy armor drains maximum speed. Pushing performance to one extreme creates a physical dead zone on our graph. A plane with maximum payload, armor, speed, and range is impossible to build. Achieving air superiority required abandoning the search for one flawless plane in favor of a strategic portfolio of specialized, compromised machines. This strategy is visible on the factory floor of the American heavy bomber campaign. The B-29 Flying Fortress prioritized defensive firepower and structural redundancy, designed specifically to bring crews home through heavily defended European airspace. That legendary toughness came at a high cost. The weight of its armor and guns severely restricted its bomb load and its maximum operational range. The B-24 Liberator offered a different solution, built with a long, narrow wingspan to carry heavier payloads over much longer distances. Prioritizing utility and range meant the B-24 was less durable in combat and more physically demanding to keep stable in formation than the B-17. Planners had to weigh these two philosophies, trading the survivability of the B-17 against the sheer destructive reach of the B-24. By 1944, the B-29 Superfortress pushed the heavy bomber into a different physical environment. Its pressurized cabins enabled it to cruise at altitudes where most enemy interceptors could not operate. Reaching these heights required a massive financial investment and complex engineering, which delayed the B-29's arrival until the very final stages of the conflict. Bomber procurement was a ruthless calculation, balancing crew survivability against the weight of explosives required to end the war. Protecting those bombers required fighters, but no single design could handle every tactical environment. This decision tree maps how different mission profiles dictated completely different engineering. High-altitude escort demanded aerodynamic efficiency and sustained speed, requirements that led to the P-51 Mustang. The Mustang's streamlined fuselage and tapered wings allowed it to slip through thin air with minimal resistance, giving it the range to protect bombers deep into enemy territory. The Mustang's efficiency relied on a liquid-cooled engine. Just one bullet to its delicate radiators could seize the engine, making it dangerously vulnerable during low-altitude strafing runs. Ground attack missions required the P-47 Thunderbolt, engineered around a massive, heavily armored radial engine with no liquid coolant pipes to sever. The Thunderbolt could absorb punishing damage and keep flying, but that heavy armor made it too large to match the agility of the Mustang at high altitude. Over-water operations in the Pacific required the P-38 Lightning, where twin engines were a necessity for pilots to survive a failure thousands of miles from the nearest runway. The safety of that second engine came at a cost. It created a much larger target for enemy gunners and required significantly more complex maintenance on the ground. Achieving total fighter superiority meant deliberately accepting severe vulnerabilities in secondary roles to guarantee dominance in primary ones. The Pacific Theater amplified these trade-offs. Launching aircraft from a tiny, moving carrier deck imposed brutal physical limits on size and weight. Naval dive bombers operated within these restrictions, executing steep, vertical dives to strike fast-moving enemy warships. Early in the war, the Navy relied on the SBD Dauntless, which featured an incredibly stable airframe for vertical diving. That stability provided the pinpoint accuracy needed to win at Midway, but the lightweight frame had a strict ceiling on the size of the bombs it could physically carry. The SB-2C Helldiver was designed to replace it, featuring a bulkier frame engineered to drop much heavier payloads against fortified targets. This scorecard highlights the compromise. Doubling the bomb load for a carrier deck ruined the aircraft's aerodynamics, making the Helldiver notoriously difficult for pilots to handle. Increasing the lethality of naval aviation pushed the mechanical limits of the aircraft and the physical endurance of the pilots. The overarching lesson of American aviation procurement is found in the breadth of the fleet, not any single design. The operating environments tell the story. The vast oceanic stretches of the Pacific demanded different hardware than the high-altitude armored combat over Europe. When we map these aircraft to their specific regions, the necessity of building dozens of distinct airframes becomes obvious. True military power resided in the system. The United States built a complementary fleet, where the ruggedness of one airframe covered the vulnerabilities of another. Declaring any single plane the best is a meaningless debate, unless you first strictly define the combat environment it has to survive in. Ultimately, victory in the air grew out of a collection of diverse, highly specialized, and imperfect tools, all working in concert. Operational efficiency is found in matching specialized, compromised engineering to an unforgiving reality.